Good afternoon, students. Yesterday, about classification of elements, simple introduction given. Shells, subshells, orbits, off-filled, completely filled. How to write electronic configuration. Ultimate shell, penultimate shell, anti-penultimate shell, core shells, inner shells, diagrammatically given. And homework given, write 1 to 30 electronic configuration, anyhow practice 1 to 30. Then after a complete classification, again I will explain that, how to write electronic configuration. Here, why do we need to classify the elements? First concept in this PT, periodic table, periodic classification of elements. What is the main necessity to classify the elements? Initially, in the beginning, that is in 1800, that is 18th century, in the year 18 centuries, there are only 31 elements were known. 31 elements are known. Here 1865, in the year 1865, almost elements discovery doubled. There are 63 elements are known. 63 elements are known. So day by day, like years together, new scientists, young scientists discovering new different elements by using natural analysis, by using their compounds. Scientists, chemistry people discovering every year some new different elements. Now today, nowadays, right now, at present, in some textbook, in this century, in some textbook, 114 elements, 117 elements, nearly 120 elements were known. So right now, at recent 21st century, right now, here nearly 120 elements. Nearly 120 elements are known here. Known elements are nearly 120 elements. All these elements are discovered by their natural analysis or by some processes. After atomic number, after atomic number 90, after atomic number 90 elements are called synthetic elements, are synthetic, or these are also called a man-made elements. These are also called trans-uranium elements. These are also called trans-uranic elements. So are the trans-uranic elements which are synthesized by transmutation process, because which are prepared by a nuclear transmutation process. By transmutation process, by nuclear or chemical process, elements are prepared. So here, day by day, elements are newly discovered elements are increasing. So after 31, 63, then 114, 117, 120 elements are right now we know. So after elements atomic number 90, some elements are not directly available in atmospheric air, which are synthesized by their compounds. Means if you know the compound, by using the compound contain what type of elements, isolated some elements by their compounds. So it is very difficult to estimate the individual elements properties or the characteristics. That's why to remember easily characteristics of each and every one individual element and their compounds properties, there is a need to classify all the known elements in a systematic manner. That is, why do we need to classify all the known elements? To remember accurately their properties systematically and their compounds properties, there is a need to classify the elements. Okay, so here on increasing number of elements, it is very difficult, it is very difficult to explain the individual properties of each element and the properties of their compounds and the properties of their compounds. There is a need to classify the all known elements. So why do we need to classify the elements? Means to remember their systematic characteristic properties, individual elements characteristic properties. We want some important classification methods. There is a need continuous here. There is a need to classify all known elements in a systematic manner. Under the name of classification of elements and periodicity in the properties of elements. So this is our chapter heading, classification of elements, or simply we can use periodic table. Okay, so there is a systematic there is a need to classify all known elements in a systematic manner under the name of classification of elements and periodicity in the properties of elements. Clear? So here Initially, elements are classified as points wise. Initially elements are classified as metals like electropositive elements. Metals means electropositive elements, and non-metals, and non-metals. There's non-metals means electronegative elements. I'll explain now at the end of this unit some important metals and non-metals, how the elements are classified. Then elements also classed on the basis of their valency. Their valency is nothing but combining capacity of an element. So the valency is nothing but here combining capacity, or the combining capacity of that element. Their valency is either maybe either maybe monovalent, bivalent, trivalent, and so on, tetravalent, and so on. Based on their combining capacity is only one, monovalent; two, valency, combining capacity bivalent; three, it is a trivalent, and so on. But there is a drawback to classify the elements on the basis of valency, because different valency elements having the same properties and having the same atomic mass. So here there is a problem to classify the elements on the basis of valency, because different valency elements have same atomic mass and same properties. Hence it was rejected. To classify the elements. So initially these are classified as metals and non-metals. There is some problem, and classified as based on their valency, combining capacity, as monovalent, bivalent, trivalent. But here if we can classify the elements on the basis of valency, are the elements, different element or different valency elements of the same atomic mass. For example, here iron is there. Iron Fe atomic number is 26. Atomic mass is 55.5, 56. Now here this iron exists as Fe plus 2 as well as Fe plus 3. It is a bivalent. It is a trivalent. This is termed as a ferrous ferrous, it is termed as a ferric. This is ic as. Lower oxidation state ions are generally S. Higher oxidation state generally termed as ic. Ferrous, ferric. So both ferrous and ferric are different valencies. Different valencies means having different properties, but not having different properties. Same properties, same atomic mass. That's why this way or the valence method to classify the elements concept was rejected. After this, there are another important methods to classify the elements. After John Dalton's atomic theory, do you know John Dalton's atomic theory? Postulated, already explained. So after next point. Next point. After Dalton's postulates like in 1800, scientists, that is chemist people, scientists took atomic mass or weight is the basic fundamental unit to classify the elements. So initially basic fundamental unit atomic mass is used. So after that atomic mass, there is another important newly modified tables are there, periodic tables are there, that is atomic number and electronic configuration. That is another concept. Initially, after Dalton's postulates in 1800, chemists people, scientists took a atomic mass is the basic fundamental unit to classify the elements. So on the basis of all these points, your first primary important law is all these elements are classified under the name of a table, that is a periodic table. What is periodic table? We'll discuss later in modern periodic table. So before that, your first important law is, that is Dobby-Reiner's triad law. This is very important. Initial basic idea given by Dobby-Reiner to classify the elements after valency and after metals and non-metals concepts. Okay. So already in lower standard, in 10th standard, given this concept, Dobby-Reiner triads. Sir, what is a triad? Tri means 3. So here Dobby-Reiner used atomic mass. Means triads mean here the 3 elements series with the atomic number relation, atomic mass relation. So are the 3 elements series concept introduced. According to this law, all known elements based on their atomic mass arranged increasing order of their atomic masses, 3 elements series. According to this, the atomic mass of a central element in a triad is equals to the arithmetic mean or average atomic masses of remaining 2 elements present in a triad. But here some triads are succeeded to explain, to classify all the known elements, but in some triads at that 1865 or 1829, nearly at that period, only nearly 65 elements only we know. all these elements are not classified under this triads concept because in some triads, atomic masses of three series elements having the same similar atomic mass, there is no change. That's why this law also rejected. So statement 1 mark maybe will ask, state Dobberainer's triads law. Very simple, I will state it. Okay, just observe it. So here to classify the all known elements, there are so many methods, so many laws, and so many scientists conducted so many experiments. Finally, right now we are using one new modern periodic table. Before that, we'll use we'll explain some important laws. That is Dobberainer's triads law. Statement like according to this, the atomic mass of a central element in a triad is equals to the ARITH, arithmetic, or average, anyone we can use, arithmetic mean of remaining two elements, that is 1 mark important statement. So according to this, the atomic mass of central element in a triad is equals to the arithmetic mean of remaining two elements, or arithmetic mean of atomic mass. That you write here arithmetic mean of atomic mass of remaining two elements in a triad. So I'll create one important table here for triads table. Some examples, 4 or 5 important examples. For example, it is a triad it is, and it is arithmetic mean of first and third element. This is. So this is one important table to explain now this important law, triads law, Dobberainer's triads law. One best example is like one triad is lithium, sodium, potassium. This is. Now lithium atomic number is 3, atomic mass is 7. This is the way to represent nucleides in a structure of atom explained. Symbol, atomic number and atomic mass. Here this is represented as that is X element anything like Z to A. This is the simple nucleide. This is simple nucleide. Atomic mass and atomic number style. Now sodium atomic number is 11, atomic mass is 23. Potassium is 19 and 39. This is one triad. Okay, so it is one triad, arithmetic mean of first and third elements in a triad. So here this is the one triad. In this triad, central element is sodium. It is mass is 23. So the atomic mass of central element in a triad is equals to the arithmetic mean of atomic masses of remaining two. That is here 7 plus 39 divided by 2, that is equals to 46 divided by 2, that is 23. This is the atomic mass of Na, sodium. This is clear. Succeeded to explain one series. Like some more important series explained, okay, no problem. But some other series, almost all are three elements having the same similar atomic masses. That's why he failed. This law was rejected to classify the all known elements. Now I'll take one more example here. That is chlorine, bromine, and iodine. This is 17, 35.5. This is 35, 80. This is 53, 127 atomic masses. Now this is the triad central element. This is. Now its average is 35.5 plus 127 divided by 2, arithmetic mean is. Now it is 0.5 it is. Now 7 plus 5, that is 12. Now remaining is 6 and here 1 divided by 2. Addition, this is point, that's right. 5 plus 7, 12. And again 2 plus 3. 2 plus 3, 5, 1 is there, 6, and remaining 1 is balanced. Now this is 2 8s are 16, like, then 1 here answers, like it is 25, 81.25 this is. So nearly here 80 equal it is. Similarly, your third example is calcium, strontium, and barium. Now it is 40, it is 88, it is 137. Atomic number is here 20, 38, it is 56. So these are the three important series, like 40 plus 137 divided by 2, that is equals to here 177 divided by 2, that is nearly 88.5 is the atomic mass of middle element, nearly strontium. So succeeded to explain all these series, but for some elements, triads series, continuously better you write in this table only. Fourth example is iron, cobalt, and nickel. Atomic numbers are different, like 26, 27, 28. Yeah, nearly 56. This is nearly 58. Here also 58 point something, 59 nearly. Now, atomic numbers are different and atomic masses not exactly same, 55.5. Nearly same, almost having the same atomic mass. So nearly all the three having nearly same atomic mass, same atomic masses. That's why he failed to explain to classify the all the known elements according to this triads concept. Like your ruthenium, rhenium, and palladium, like here osmium, iridium and platinum also having same nearly same atomic masses. Same atomic masses. It also nearly same atomic mass. Atomic masses. That's why one of the most important drawback for this is due to the same atomic masses in a triad. This law was rejected. After this law, there are another important so many laws. Next important law after this, yeah, a simple conclusion, that is drawback, demerit, drawback of Dobie-Reiners. Dobie-Reiners triads law. What is the important drawback, or simply write demerit? In some triads, almost all three elements have same atomic mass. Hence, this law was rejected. Hence, this law was rejected. So in a lower standard, either in ICSE or in a state board or in CBSE, given this law, Dobie-Reiner triads law, very simple concept given. Here somewhat elaborated concept. Some more one or two extra points given. Why it is rejected? Due to the nearly same atomic masses. And in layer standard, in 10th standard, there is another direct concept is Newland octaves law is there. But in PU level, 11th standard, in between Dobie-Reiner triads law and Newland's one more important simple law, I'll give just one line only for that, just to note down that. Okay, that law is after this. Another important second law is AEB D. Chan Courtiers law. This is not a popular important law. Anyhow, in our textbook, NCERT textbook given this important law. So after Dobie-Reiners introduced one more important scientist, nearly 1865 in the year introduced one more important law by D. Chan Courtiers important law. He did a very simple explanation by using a cylindrical chart arranged, and he took a atomic mass is the basic unit to classify the all known elements. Okay, so here he took atomic mass as the basic unit, and all known elements arranged according to increasing order of atomic mass on cylinder type with 16 equidistance lines, vertical lines on cylindrical cylindrical shaped chart. Due to some problems, this law also rejected. Enough. No need extra information about this law. Just simple words given about this. Means AB D. Chan Curtius law. Main important concepts. Just a design on chart, just like a cylinder shape like this, and divide the chart into a 16 equidistant vertical lines, and all the elements are arranged according to their atomic number. But there are some important problems. Problems means to explain their properties, physical and chemical properties. There are some important problems. That's why this law also rejected. So another important law, well-known law, we know already, that is Newland octaves. Very, very important. We know already in a lower standard, that is in a 10th standard. Third important law is, third one is Newland's octave law. So the Newland, after this D. Chan Curtius, introduced one more important law. By using atomic mass only, all the known elements are arranged increasing order of their atomic masses. According to this, properties of every eighth element properties are similar to the properties of the first element, just like a eighth musical note on a musical scale. Just I'll write down important statement, then afterwards I'll explain on flow chart how it similar their properties. Okay, note on this. According to this, according ACC is nothing but according to this, properties of every eighth element, properties of every eighth element are similar to that of first element, just like eighth musical note on musical scale, when they are arranged, according to increasing order of atomic masses. So here are elements, some known elements at that time. All the elements are arranged by using atomic masses. So here in some textbooks, some different tables given. Here an important table for that Newland octaves. I'll create an important simple scale, that is. Here the musical scale, on musical scale there is a sa, re, ga, ma, pa, dha, ni. This is like it is 1, 2, 3, 4, 5, 6, 7. Now here musical scale is like, now this is sa, re, ga, ma, pa, da, ni. So after this ni, again that musical scale note again start with sa, like sa, re, like this. So here based on their musical scale notes, we can create like this. This is created as a first group. Like this is hydrogen. This is lithium. Like hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen. So hydrogen, helium is not there here. According, that is a new periodic table, modern periodic table. But people are think about, sir, after hydrogen there is another important element, helium is there. Don't bother about right now perfect long form of the periodic table. These are just one ideas given to classify the elements, basic class. So here the hydrogen, then there is no helium, lithium, beryllium, boron, carbon, nitrogen and oxygen. Increasing order of their atomic masses arranged just like sa, re, ga, ma, pa, dha, ni. After 7th, 8th element again repeats the properties of this. That's why according to this, the properties of every 8th element at the time of Newland are similar to that of properties, similar to that of first element properties. First element properties, just like 8th musical note on a musical scale. See here, sa, re, ga, ma, pa, dha, ni. Then again 8th note is sa, start again. That's why here it is fluorine. After fluorine there is no neon, it is a sodium, magnesium, this is aluminium, this is silicon, this is the phosphorus, sulfur, this is. So here the, after sodium, magnesium, aluminium, silicon, phosphorus and sulfur, again there is another important, that is chlorine, this is. There is no argon. It is potassium, beryllium, magnesium, calcium it is. Boron, aluminium, here boron, aluminium, it is again start one more, originally gallium, but it is not there. So after this, your elements are here actually it is boron, aluminium, gallium, but here chromium is there. Or here some elements like iron element is present, here manganese is present, here titanium is present, like. So here the properties of manganese are not similar with nitrogen and phosphorus. Our chromium properties are not similar with aluminium and boron properties are not similar. But the properties of beryllium, magnesium, calcium are similar. That's why this is the atomic number 20. So after atomic number 20, Newland failed to explain the classification of elements. Because at the time the known elements are arranged like this. These are the D block elements. Here the properties of this chromium and boron, aluminium are not similar. So if you can follow this method, musical note method, won't get accurate properties, similar properties. That's why these laws failed to explain the classification of elements. Clear? So here simple 2 minutes. This law, why this law is it was rejected means simple drawback. Simple drawback or the demerit of this law is after atomic number After atomic number 20, that is Ca calcium, this law was rejected because there are some important reason because are the properties of simple reason manganese are not similar with the properties of nitrogen and phosphorus. That's why it was rejected. Clear? So here today three important PU laws completed. One is Dobereiner's triads law. Second one is AEB D. Chan-Curtius. Third one is Newland octaves law. Tomorrow some more